Right, what up, everybody? Today we're going to be talking about electrostatics, and electrostatics has to do with electric charges. So there are two types of electric charges. There are positive charges, and there are negative charges, right? Now, most objects tend to be neutral, right? And what does neutral mean? Neutral means that there are just as many positive and negative charges. So, for instance, this object on the left, made up of all these electric charges, would be neutral because it has 8 positive charges and 8 negative charges. And so a way you can calculate the net charge is just to add those together, and negative 8 plus a positive 8 gives you 0. So it would be a neutral object. Now the object on the right, you'll see, has more positive charges than negative charges. Has 6 negatives and 10 positives. So what would the net charge be? The net charge would be negative 6 plus 10, which is a positive 4. Right, so we would say that this was a positively charged object. There's more positive charges than negative charges. Now, in the real world, objects are made of trillions upon trillions of charges, and typically for most objects, the number of negative and positive charges are equal or very, very close, so much that you don't notice a electric charge in them. Right, but some objects do have significantly more positive or significantly more negative charges, and we call those positively charged objects or negatively charged objects. Right. So this next part is pretty much important to understanding how charges move, and that is that positive and negative charges are attracted to each other if they're opposite. They're repelled if they're the same. Right. So if there's two charges that are both positive or both negative, they'll be pushing away from each other. And if there's a positive and negative object, they'll be pushing towards each other. Right now, Newton's third law still applies here, which says that for every action, there's an equal and opposite reaction. So in each of these cases, both charges feel the same force, but they feel it in different directions. So when the positive charge and negative charge comes together, you can see that this positive charge feels a force pulling it to the right towards negative charge. The negative charge would feel the same amount of force, but it'd be pulling it to the left, right? So they're going in different directions, but their forces are equal in size, right? And with the like charges, they say these two positive charges are repelled by each other. The charge on the left feels a force from the charge on the right, pushing it away, which in this case would be the left. The other positive charge over here feels the same strength of force, but pushing it to the right. So the charges are equal and opposite, in the same way with the two negatives. So opposites attract and like charges repel. And this is a case for like individual charges, but it's also the case for objects. If one object has a net charge that's positive and another object has a net charge that's negative, those two objects are going to experience a force pulling them together. Whereas if two objects are both have a net charge that are positive, they would feel, or a net charge that was negative, they would feel a force pushing them apart. All right, where do these electric charges come from? Well, they come from, as you learn in chemistry, they come from individual atoms. Right, individual atoms have protons and neutrons and electrons. The neutrons don't have a charge, but the protons have a positive charge, and the electrons have a negative charge. Right. Now, as long as a atom has the same number of protons and electrons, then that atom is neutral. It does not have a net charge, so it doesn't contribute to the net charge of an object. However, atoms can lose or gain electrons. If they lose electrons, that will give the atom a positive charge, because now they have more protons than electrons. If they gain an electron, that'll give it a negative charge. Okay, so here's an example of an atom that has 6 electrons and 6 protons, so its net charge would be 0. It would be it'd be neutral. All right, but here's another example where this atom has gained an extra electron over here, has 3 electrons and 2 protons. If you add them together, you get that it has a net charge of -1. Okay, so this atom would attract another atom that has a positive next charge, and it would push away another atom that has a negative charge. Okay, so obviously with atoms, we don't really see it because atoms are so small, but when there are trillions and trillions of charges going around, we can actually see things. So an example is lightning, right? So in lightning, um, in an individual cloud, because of the disturbance that's going on in the cloud, you could have a lot of the electrons move to one side of the cloud or the other, right? And if they move to the top of the cloud, that creates a positively charged bottom of the cloud. And if they move to the bottom of the cloud, that creates a negatively charged bottom of the cloud. And what happens is, if the ground, and as we'll see in just a minute, the surface of the ground becomes positive, the electrons are attracted to the ground, but there's a bunch of air in the way, so they can't get there until enough of them get together that the force is so strong that they can overcome that gap in between the cloud and the ground and actually come to the ground. And that's why lightning is such a big surge of electricity, is because it takes a lot of the electrons to do that. You took a look at this the other day, where there's a sweater, a balloon, and a wall. And you'll notice that all 3 of these are neutral objects right now because they all have the same number of positive and negative electrons. So if you move the balloon to the sweater, right, you'll see that the balloon picks up electrons from the sweater. And the reason is just that the rubber on the balloon is better at grabbing electrons, and the wool on the sweater is not very good at holding on to the electrons. And so it's just a matter of what materials they're made out of. But once the balloon has all these negative charges on it, then the net charge of the balloon is negative, right? And because the sweater has lost electric charges, its net charge is positive. So because one object's negative, one object's positive, they're now attracted to each other, right? Electric charge in everyday objects is not really that strong, but with something like a balloon that's very light, that force is big enough to actually cause the balloon to move a certain way and actually stick to something. All right, now what about the wall? Okay, would the negative balloon stick to the neutral wall? Right, because we haven't said anything about what happens between negative and neutral objects. Well, nothing per se. There's nothing per se that says that a neutral object is attracted to a negative object. However, look what happens as we move the balloon closer to the wall. You'll see that the negative charges in the wall move away. Okay, and when they do, and the reason they're moving away is because they're repelled by the negative charges in the balloon, because the balloon is negative, and 2 negatives will be repelled by each other. And so the electrons that are free to move inside the wall are going to move further and further into the wall, and that leaves a positively charged surface. So now the positively charged surface is attracted to the negatively charged balloon, right? So negatives and neutrals don't attract, but negatives and positives do, right? And when you have material where the electrons are pretty much free to move, at least enough, then you'll see that charged objects actually do stick to those neutral objects. And it's because it creates a positive surface. Right. It is important. You'll notice that these protons never move, right? It's very difficult for protons to be transferred from one thing to another, whereas it's very easy for electrons to go from one thing to another. So We talk about charge transfer. It's always going to be the electrons moving, and if the electrons, which are the negatively charged particles, move from a one object to another, the object that they leave is positive, and the object that they arrive on will become negative. All right, so on Monday you did the tape example. You're probably wondering what type of wizardry caused the two pieces of tape to stick together. Right. So this is what happened. All right. You had for those of you who didn't do it, you had a piece of tape that was pressed down on the table, and then a second piece of tape was pressed down on top of that tape. So we'll call the tape on top tape one, and the tape on the bottom tape two. All right. So at first they're both neutral, same amount of positive and negative charges. Um, but when you pull up on the top tape has a sticky part that is good at grabbing electrons. And so it was the sticky part of the top was ripping electrons off of the top of the bottom tape, right? And so that means the tape on top now has more negative charges than positive charges. And the tape on the bottom has more positive charges than negative charges. Right? So that makes the tape on top positive and the tape on the bottom negative. So what's going to happen? Well, the negative tape is going to be attracted to the positive tape because the negative tape is a negative object and the negatively charged object, and the other tape is a positively charged object. So they're going to be attracted to each other. So that's why you saw the two pieces of tape that were attracted to each other, right? And also in the experiment, I think you took two negative tapes and saw what they did, and they pushed each other apart. But anytime you saw the two pieces of tape move together, you had two oppositely charged